whatever that you want to share. You don't necessarily need, to be connected to a switch that's configured with IP settings and what have you. You can just enable ad hoc services on your mobile devices or laptop devices, and then help address your transfer needs or sharing of movie files or documents needs. Okay, so this is a good approach to framing some of these uh, transmission needs, separate transmission needs, in a sense, which means you're pretty much limited to whatever information is being shared within just the participants of the ad hoc network. So with all these applications from configurations and what have you, um, there has to be some requirements before really establish a good wireless LAN. You do need some requirements. Some requirement must be met. Otherwise, wireless transmissions wouldn't really serve their purpose very well. Okay, so there are some key requirements that we need to look at if you really want to address wireless LAN. So at least the solution is not useless, but actually can address a specific need for which it was designed for or was meant for. Okay, so let's go some of those. Uh, the, the the first one will probably be, I'll say, throughput. Throughput will probably be the first. Yes, throughput will probably be your first thing, which is making mediums access control protocols as efficient as possible to maximize capacity. Um, Generally, we're looking at when we talk about throughput, we're looking at how well can you maximize the medium so you can get the highest capacity out of it or the maximum capacity out of it. Okay, so that's one thing that you have to look, one requirement that you need to keep in mind when it comes to wireless LAN implementations. You have to look at, can I address, throughput? Can I get the maximum capacity out of that transmission medium? The other one is the number of nodes, which is how many number of devices can you support across a multiple cell. Uh, Take for instance, when you go way back to your cellular wireless network, every cell has got a number of devices that it can support based on the frequency allocated. Okay, they're now like unlimited, right? So obviously the number of nodes um, is a key requirement. How many devices can you support within a given cell? When you talk about your Wi-Fi devices, most of your Wi-Fi, your basic Wi-Fi setups or configurations do support maximum of 25 to 30. The highest you can go is about 50 on any wireless device. In terms of Wi-Fi, your pure 2.4 gigahertz frequency Wi-Fi devices. When you do configure it, the maximum you can get is about 25. To get a really good throughput, 25. You can get by, at, at the maximum of 50. Anything above that, it's going to be a huge problem. You know, a lot of transmission problems that start coming into play. You know, because looking at the throughputs, most wireless devices, Wi-Fi devices, supports about 54 megabit per second. So if you were to support, 50 device maximum, one device taking about 1 meg basically, right? Out of the 54 megabit per second. Yeah, but if you want the users to get a better experience, 25. So at least everybody gets about 2 meg, at least 2 meg to work with. Okay? The other one is connection to backbone line. That's the wireless LAN as a backbone. It's a really good high-speed backbone to allow for information transmission to be seamless. So here we're looking at interconnections with wide backbone stations with various control modules to help make the transmission or the user experience much more efficient or much more reliable. We also look at service area. The coverage is very important. How much coverage can your wireless LAN cover? You have to think about some of these as a requirement. What do you need? If you're going to support a given radius, the question is how how big should that radius be? In this case, most average coverage for wireless LAN requirements should be within hundreds to 300 meters. When you start going beyond that, and you're looking at signal degradation, called drops and what have you. The other requirement is battery power consumption. As you know, uh, your transmitters or your antennas with your transmitters or your transceivers built into them uh, are, are only efficient based on the power requirements that it supports. Okay, it's the power requirement it supports that can make that device either um, efficient or not. Okay, so we generally when we talk about power consumption or battery power consumption, we want to look at how reduced power consumption is within the particular wireless LAN, especially when it comes to um, how much they use. Today we want to save as much power as possible. One device is to use less power as possible. But also, provide the maximum transmission need that we need, that we want. Okay, so we're looking at what can you use minimal power uh, to address your transmission, as well as not using so much power when the device is not being used. So in this case, is there a way to put the devices into a sleep mode? So in case it's not being used or it's an idle state, you can basically minimize its power consumption. So it's a good requirement of it because power is becoming quite essential, very, very limited these days, especially when you're within a country or a region where energy is it's a luxury. It's not easily accessible or it's quite expensive. Then wireless devices or wireless LAN implementations must also look at some of those uh, 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 priorities. Must really look at it very carefully to see if it can meet those requirement needs or to make sure that it can design those systems or applications or devices to meet that environment need. You know, these days phones have been designed such a way they use less power, but still address a number of your transmission needs. Okay, so key requirements, very very huge requirements: battery power consumption. How much battery power some of these devices use for the wireless LAN implementation. If your wireless LAN implementation is going to use up a ton of megawatts of power, then there's no point, especially when you're within an environment where power supply is quite expensive or scarce, then you want to rethink your wireless LAN implementation again or all over again. Other requirements, so these are your main key requirements. Other requirements are transmission robustness and security. that is permitting reliable transmission within noisy environments and security from eavesdropping. We're looking at ways to make sure signals are not intersected easily by hackers, or eavesdrop by hackers and steal information. How well can you secure it? How well is the wireless LAN going to be robust? How robust is it? Okay, so requirements is you're looking at requirements over here. It's some of the things that you be looking at. Because eavesdropping and security in general is a huge problem with wireless transmission, especially if you transmitting sensitive information, like from bank transactions, via point-to-point radio links from maybe the HQ head office or headquarters to branch locations. Robustness and security is a huge requirement over here. Co-located network operations is another one where you look at whether the wireless LAN can support two or more wireless LANs within a given area, within the same area. Okay, generally co-located is operations for two or more wireless LANs within the same area, and it's supported. License-free operation. If you've come across, if you read through the spectrums back in Datacom 1, you will know that some spectrums are more or less unlicensed, and some spectrums are licensed. Most of the ones that you use for your cellular networks are purely licensed. The ones that you use for your home Wi-Fi services are unlicensed. So obviously, when you're implementing a LAN network or a wireless LAN, you have to consider what kind of licensing mode you want to operate within. Okay, so here the license-free operations is the use of wireless LAN products without secure license frequency bands. Hands-off roaming, which is movement of mobile stations within cells that support it, or is that wireless LAN going to support that? So that when you're moving from cell to cell, uh, within cellular wireless networks, the question is how dynamic or how fluid is the handoff or roaming being processed, and will that device or wireless LAN support it? Configurations within dynamic levels. Generally, we want to look at if your transmission or your implementation um, can permit dynamic and automated additions of uh, end systems, including deletions and relocations without interruptions. Can you add automatically? Can the system add like what's a number of your cellular stations do? MTSOs, the control unit, is able to uh, take out cell devices or handsets as and when they move out of a given cell to make room for other devices to come through. And all of that is done automatically, not manually. So does the system support that dynamic and automated addition or deletion, or even relocation of end systems from one node to another, from one cell to another? Okay, so dynamically done. If so, you have to actually look at what kind of requirements goes with that. Now let's move on to technologies in terms of wireless LANs. Two main technologies are within wireless LANs. The first one is your infrared LANs, which is where you create an individual cell of an RF LAN, which is limited to a single room, mostly because infrared light does not penetrate uh, big or thick structures or concrete or opaque structures. So generally, one technology that you have within wireless LAN is infrared, where individual cells use RF or infrared signals to create a LAN. Nowhere it's limited within just a single room or a single structure. The other one is the spread spectrum, which is where you use your uh, frequency radios or frequency spectrums to address your transmission needs. It happens to be the spread spectrum length happens to be the most widely and popular type of wireless LAN technology. Oh, it's over here. Okay, so yeah, it's the most popular type, and some of the examples that we have are microwave bands for online system ones or wireless LANs. We do have your in terms of band frequencies for the unlicensed, we do have 915 megahertz bands, which ranges from 902 to 924 megahertz, with a maximum bandwidth of 26 megahertz bandwidth. And then you do have your these are the unlicensed ones. Okay, the unlicensed microwave bands for wireless LANs. 915 megahertz bands, the 2.4 megahertz band, which is mostly for your Wi-Fi these days. The 5.8 are for your point-to-point as well as your uh, what other services? High bandwidth transmission needs, you know, for even for some house phone devices or other microwave systems. They fall within the 5.8 gigahertz bands. And like I pointed out earlier, these three microwave bands are on lenses that could be used for wireless LAN implementations. Okay, so you also notice the bandwidth that comes with it. For 2.4914, you have 24 megahertz bandwidth. For 2.4, which is your Wi-Fi services or Wi-Fi system that you set up, either at home or using your mobile devices, they support up to 83.5 megahertz bandwidth. And then for much higher bandwidth, you're looking at the 5.8 gigahertz bands. Standards that goes with wireless LANs revolves around the IEEE 802.11 standard, which plays a key role in how devices or systems conform to the IEEE standards or IEEE consortiums. The IEEE 803, so 802.11 happens to be a devoted standard for wireless LANs, and it consists of mostly your MAC and your physical layer, which means they operate at the last two layers of the OSI model. Um, Wi-Fi Alliance, which is your wireless fidelity, is also another industry consortium that helps with their particular standard. So we're looking at various standards that goes with the that goes with wireless transmission or wireless implementation, and the general standard is falls under the IEEE 802.11. So it's purely devoted for when we're talking about wireless, everything revolves within the IEEE 802.11, not 803. 803 is for the high-speed LANs, if you remember. So 802.83 or whatever revolves around the Ethernet, right? High-speed Ethernet. But pure 802.11 is purely wireless implementation. And we do have wireless fidelity, which is on a consortium that falls within the same standard. It's usually designed to certify interoperability for Wi-Fi devices or for 802.11 products, which could be your Wi-Fi device, your wireless antenna, routers, your home wireless antennas, uh, or wireless routers or device or switch or whatever it is. Okay, so that's the Wireless Fidelity Standard or Alliance Consortium. And then when it comes to the architecture, the smallest building block happens to be the basic service set. We'll look at that a bit more, but generally, the smallest building block forms the architecture for the 802.11 IEEE standard for Wi-Fi or for wireless standards. And the smallest building block is your basic service set. It's called the basic service set. Happens to have a number of stations executing the same MAC protocols. They share wireless mediums, and most of the basic service sets corresponds to a given cell. A typical basic service set may be isolated or may connect to a backbone distribution system through an access point, and the job of that is to basically create a bridge through an access point. So generally we say the access point functions as a bridge and support relays or as a relay point. So basic service sets can interconnect to the backbone distribution systems. The access point can also support stations which has the logic to provide other distribution services. And then you do also have your access points handling correspondence to and from your control modules. So we're looking at some of the key roles that an access point plays within a given basic service set to either isolate or connect to backbone distribution systems or distribution systems. And distribution systems can either be a switch, wired network, or a wireless network. The other service set, it happens to be your extended one, which consists of two or more basic service sets. So in general, you could say if you to connect two or more basic service sets through a distribution system, you'd have what you call an extended service set. So I think the next slide we do have a diagram of the architecture. So this is some of the basic set, the small building blocks, more summary levels. And there's a diagram that basically talks to you about the architecture. So we're looking at the architecture. We'll look at the basic service sets, access points, and extended service sets. So your extended service sets, which consists of multiple basic service sets interconnected to a distribution system to help with transmissions for that can accommodate wireless LANs. So here you have a number of basic service sets that supports APs. For this segment and for that segment, all linked up to the distribution system that interconnects to other LAN networks. And then you do have, in all, you do create what you call an extended service sets. So if you have multiple basic service sets interconnected via distribution system, you form what? Extended service sets. Protocol architecture, we're looking at the logical link control and how they interface with the MAC layer from port coordination functionalities to your conventional services for distribution coordination functions, and the various technologies that goes with it. You have your frequency bands, your 2.4 gigahertz, your infrared, and 5 gigahertz that supports various frequency channels or distribution service sets. Now let's look at the physical layer. Obviously, we're looking at the architecture and the applications as well as the configurations and what have you. Let's look at the physical layer of the typical wireless LAN. So in a way, you could say the architecture, the configurations are within the data link layer or the MAC layer part. Now we look at the physical layer of it to see what goes, what's involved at that level. The physical layer was issued, well, actually, it's issued in 4 stages. The first part was in 1997 when IEEE 802.11 was formed and was designed to include MAC layers and 3 physical layer specifications, 2 for your 2.4 gigahertz bands and 1 for infrared. Now they all operate at 1 or 2 megahertz per second. As I mentioned earlier on, most wireless systems or 2.4 gigahertz transmission can only support 54 uh, uh, megabits per second transmission. And the number of capacity they can go with that is maximum and to get a most efficient or much uh, fluid connectivity or functionality or purpose or for lack of a better word capacity out of that 25 users is the most that you could fit within that. So hence all operations do support 1 to 2 megabit per second. Oh, okay, let's go through that. Yeah, so you do have 2.4 gigahertz bands infrared, and then all operations supports 1 and 2. Now the second part happens to be 2 additional ones, which were the IEEE 802.11a. So the initial one was just 802.11 generalized, but with time they realized the transmission needs had data rates that needed to be either worked up in terms of the unlicensed frequency bands that we have. So 2 additional parts were added, and that was A and B. So you do have, if you remember, you have um, uh, you had Wi-Fi A and B, and today we have G, which combines the A and B, and then N as well. They are basically just the part of the 4 stages issued at the physical layer for most wireless LANs. Okay, so A was supposed to support the 5 gigahertz band with a data rate of up to 54 megabit per second, and the B was supposed to be for 2.4 gigahertz bands with data rates of about 5.5 and 11 megabits per second. Now, in most recent times, from 2002 and up, you notice you have the G's and that supports higher, much more higher bandwidth. And the current one happens to be the N, which has data rates in hundreds of megabits per second transmission. Quite impressive today. To think about how far it's come within the stages of the physical layer of the IEEE 802.11. The media access control itself, which is your Mac layer, has got three functions. It's one of the key function is reliability.